This is a video from the Exam 2 Review Part 1. Let's take a look at number 4. Let W equal the set of all vectors A, B, C in R3 such that B equals A plus C plus 1. So if I take the first component and add it to the third component and then add 1, you get the second component. Is W a subspace of R3? So that's a question mark. The answer turns out to be no. So the vector 1, 4, 2 and the vector 2, 7, 4 belong to W, since vectors 1, 4, 2 and 2, 7, 4 belong to R3, and 4, the second component, equals 1 plus 2 plus 1, and then 7 equals 2 plus 4 plus 1. But here's the problem. Add up those two vectors. So I'm going to take vector 1, 4, 2 and add it to vector 2, 7, 4. This is equal to the vector 3, 11, 6. And that doesn't belong to W because if I take 3 plus 6, take the first component, add it to the third component, and then add 1, you don't get 11 back. And so, therefore, the vector 1, 4, 2 plus the vector 2, 7, 4 doesn't belong to W, and W is not closed under addition. And we can then say W is not a subspace of R3. Now, let's take a look at 5. Let W equal the set of all vectors, we'll say it this way, the set of all vectors A, B, C that belong to R3 such that if we look at the third component, you get 0. So the third component has to be 0. Now, let me show you what that looks like. One other thing. Is W a subspace of R3? It turns out the answer is yes. Now, 0, 0, 0, right, belongs to W, right? Now notice, 0, 0, 0 is in R3 and the third component is 0, right? So we're okay. And so therefore, W is non-empty. We'll call it U1, V1, 0, and U2, V2, 0 belong to W, and we're going to let K be a scalar. Now, let's go ahead and check close under vector addition. So we're going to add up those two vectors. So you get U1, so we're going to, let's try that again. So let's take the vector U1, V1, 0, and add the vector U2, V2, 0. Well, this is equal to the vector U1 plus U2, V1 plus V2, 0 plus 0, which is equal to the vector U1 plus U2, V1 plus V2, 0. And that belongs to W because notice how the third component is 0 and that vector is in R3, right? And so that implies the vector U1, V1, 0 plus vector u2, v2, 0 belongs to w. And so w is closed under addition. I hope that makes sense. Second step. If I take k times u1, v1, 0, right? Does that vector belong to w? The answer is yes, but we have to show it. So this is the vector ku1, kv1, k times 0, right? But this is the vector ku1, kv1, 0, which belongs to w. And so that implies k times u1, v1, 0 belongs to w, and w is closed under scalar multiplication. And so can we agree the subspace test tells me that w is a subspace of R3. And you're done. That one was problem number 5. Let's take a look at problem 6. Let w equal all vectors of the form, and the form is A1, 1. So the second component is 1, the third component is 1. Okay? Okay. From here, now 1, 1, 1 belongs to w. Here, before we start, let's make sure we're all on the same page. Is w a subspace of R3? The answer is no. Now, 1, 1, 1 belongs to w, right? There's lots of options here. If I take 5 times the vector 1, 1, 1, you get the vector 5, 5, 5. And that doesn't belong to w because 5, 5, 5 is not of the form A1, 1. Therefore, 5 times 1, 1, 1 doesn't belong to w. And so w is not a subspace of R3. That's a good problem, right? Because notice w is not closed under scalar multiplication. So that's okay. Now, let's take a look at this one. So you might notice on the exam, I'm going to ask you to show there's a variety of circumstances, right? But I want to show whether or not a certain set is a subspace of a vector space. I'm going to ask, okay? Now, let w equal the set of all n by n matrices such that the determinant of A equals 0. The question, is W a subspace of the set of all n by n matrices? The answer is no. Okay. Now, what's the culprit? Now, what I'm going to do is I'm going to let A equal this given matrix. So I'm going to put a 1 in the upper left-hand corner, and then I'm going to have 0, 0 all the way down. Then I'm going to go 0, 1, 0, 0, and then we'll do it again. 0, 0, 1, 0, and then when we get to the bottom, it's going to be 0, 0, 0, 0. Now, A is both an upper and lower triangular matrix. Now, notice, A is n by n, and, right, such that, essentially, and. If I take the determinant of A, you get 0. And so, therefore, A belongs to W. Now, let's take a look at B. When I look at B, I'm going to have the first row be all zeros. In the second row, I'm going to have 0, 1, 0. In the third row, 0, 0, 1, 0. And when we go all the way down, we get 0, 0, 0, 1. B is n by n, and the determinant of B is 0, because we have one entry along the main diagonal that's 0, right? And so, therefore, B belongs to W. The determinant of A plus B is, now, here, before we do that, maybe this is easier. Let's just take A plus B and add them. If I take A plus B, what do you get? Well, notice how this first entry here is 0. This first entry here is 1. So when we add them, we get 1. And then I get 0, 0, 0. And then if I take 1 and I add 1, I get 2. So I get 0, 2, 0, 0, 0, 0, 2, 0, right? And then when we get all the way to the bottom, right, the bottom right-hand corner, notice how that's a 1 and that's a 0. And when we add them up, we get 0, 0, 0 with a 1 there. Now, regardless, now look, A plus B is absolutely n by n, right? Adding two matrices of the same dimension doesn't change the dimension of the matrix. But the determinant of A plus B doesn't equal 0. So A plus B does not belong to W. And so W is not closed under addition. So when we take two matrices in W and add them, the determinant is not preserved. We're not going to get 0 back always. And so therefore, W is not a subspace of the set of all n by n matrices. Um, that's a good stopping point for this video. We did the exam 2 review part 1, and we did problems 4, 5, 6, and 7. And okay, thank you.